Hello, my name is Mingze Gayo. I am happy to share my recent work on the integrated modeling of cracking during deep penetration laser welding of nickel alloys.
The high-power laser welding represents an attractive pathway to improve the welding productivity by achieving weld penetration of nearly 10 millimeters in a single pass. And here is one of the examples for the welding of Inconel 740H. You can see from this image, if we use arc welding or even arc laser hybrid mode welding, we can typically achieve the penetration of around 2 millimeters. As we start using laser welding with relatively low laser powers, we can increase the penetration to around 4 millimeters. As we start using high power laser welding, and here by high power, I mean the laser power on the order of 10 kilowatts, and in such case, we can increase the penetration to nearly 10 millimeters in a single pass, which can definitely help us to improve the welding productivity. However, the unique process conditions during high-power laser welding can also induce defects, which were not observed under arc or low-power laser welding conditions. For example, during low-power laser welding of Inconel 740H and Inconel 690, there is no cracking occurred for both of the alloy. However, as we start using high-power laser welding, we can see this horizontal solidification cracking in Inconel 740H, while no such cracking for Inconel 690. That means that the solidification cracking susceptibility varies not only between alloys, but also with different welding conditions. One of the most accepted solidification cracking theory is called liquid fracture theory. So what happened here is, during welding process, we have different regions. For example, in the weld pool, we have full of pure liquid. And in between the pure liquid and the pure solid, we have a region called mesh zone region. So this region is a mixture of both liquid and solid, especially at the last stage of solidification, where we have the solid fraction above 0.9. So what happened here is, there will be some separations in between the solidifying materials induced by the solidification shrinkage or thermal shrinkage, and some voids may form in between these solidifying materials. And at this time, if the remaining liquid is insufficient, or the liquid has hard time to flow into those regions to accommodate the separation, solidification cracking will occur. And a more recent finding indicated that for solidification cracking to occur, we not only need the material to be in tension, but also the solidifying materials need to be stretched away from each other fast enough. And this property can be quantified by the strain rate experienced by the solidifying materials. So here I just showed one of the examples for the welding of Inconel 718. So you can see when the strain rate is very low, no cracking is going to occur, and only when the strain rate is higher than the specific value, cracking can occur. And we can call this specific value as a critical strain rate value, which is ranging between 0.011 to 0.0191 per second for nickel alloys. So the solidification cracking susceptibility is usually evaluated through the weldability tests, and these tests are mostly under arc welding conditions, and the susceptibility is usually quantified by the crack lengths on top surface of the weld. For example, in a very stringent weldability test, during welding process, there are some bending process acting on the substrate, which induce the stress or strain rate to the weld, and we can see how the alloy is going to resist cracking or not. In the other test, the transverse motion weldability test, during welding process, there are two sheets to be welded together. The upper sheet can be fixed on the substrate, while the lower sheet can be moved with different speeds to generate different deformation rates or strain rates to the weld, and we can see how the material can resist cracking or not. So we can see from these tests, the stress or strain rate which induced cracking is mostly externally applied, which sometimes cannot capture the cracking behaviors in some other welding conditions, and specifically the high power laser welding of thick section structures. To overcome this limitation, here in this work, a new methodology has been developed which is able to combine different components of the cracking issue, such as the alloy composition, process conditions, and the stress state to better understand the solidification cracking behaviors. To understand the different solidification cracking susceptibility of different alloys, we need to firstly look at their alloy compositions. So you can see between this 690 and 740H, there are some major differences between the alloy composition, such as the concentration of cobalt, iron, or some other elements. And one of the important impacts of this is these two alloys displayed different thermophysical properties. And one of the big difference here is these two alloys displayed very different solidification temperature range. You can see the Inconel 740H has nearly 4 times larger solidification temperature range compared with the 690. So this larger solidification temperature range can induce a larger matrix zone size during welding process and increase the chance for solidification cracking. To capture the process conditions during welding process, a well-tested three-dimensional heat transfer and fluid flow model was employed. What this model is doing here is it solves the equations for the conservation of momentum, mass, and energy. And then by applying some of the boundary conditions, such as the temperatures or heat flux on different surfaces, we can eventually calculate the temperature field in the weld. To validate our model, we can also extract the cross-section from the model and compare it with the experimentally determined cross-section. And this type of matching indicates that our model is able to capture the overall weld geometry, and we can also extract some important process conditions such as the thermal histories and solidification conditions out of the model. To capture the stress state in the welds, we also need to couple this thermal model with a mechanical model. What we did here is to use the calculated temperature field as an input to solve the resulting stress state using a commercial finite element model in Abacus. So basically, we can output the temperature field in terms of a point cloud data file, and then do the mapping for the temperature field on the finite element model to solve the resultant stress state. There are also some important input variables, such as the yield stress, Young's modulus, and the coefficient of thermal expansion. So these properties are all temperature-dependent properties, and this information was obtained from the alloy manufacturer. We can then start comparing the process conditions and the stress state between the two alloys. As you can see from these temperature fields, the Inconel 740H displayed much longer weld pool compared with Inconel 690, and that is driven by the larger solidification temperature range, which also induced larger matrix zone size. And also, because of the complex interactions between the temperature field and material properties, the Inconel 740H also displayed much higher stress levels compared with Inconel 690. So even though we are able to calculate the stress state along x, y, z directions, essentially what we need here is the stress level normal to the solidification direction, because that is the stress that really separates the adjacent dendrites. So the solidification direction can be determined based on the principal heat flow direction, which can be obtained from the heat transfer model. And once the solidification direction can be determined, we can start doing a three-dimensional stress transformation using the correlations on the right side to solve the stress state normal to the solidification direction, which is the sigma n in this case. And also, a special interest was given to the locations where we have solid fraction equals to 0.9, because beyond that, the remaining liquid will be insufficient, and those regions are the most susceptible regions to solidification cracking. So then we can start looking at how the stress and strain rate vary from top to bottom of the weld for different alloys. So we know that for solidification cracking to occur, the solidifying materials need to be in tension. That means the stress needs to be positive. On the other hand, we also know that for solidification cracking to occur, the solidifying materials needs to be stretched away from each other fast enough. That means we also need sufficiently high strain rate. So essentially, solidification cracking will occur at the region where we have both tensile stress and sufficiently high strain rate. And that range is around 0.9 mm for Inconel 740H and there is a power of 7.5 kilowatts, as indicated by the simulated crack range. And this range can also be validated with the actual crack range measured by micro-CT scanning. And by comparison, there just no such depths exist for Inconel 690, which explained why no cracking occur for this material even under the same welding conditions. We can then extend the calculation to some other welding conditions and basically different laser powers in this case. So we can see from this plot, the simulated crack range matched pretty well with the experimentally determined crack range, which indicates that our model is able to capture the conditions driving the unique solidification cracking behaviors during high-power laser welding of nickel alloys. Lastly, I want to provide a summary and a few conclusions on this work. So, the high-power laser welding can help us to improve the welding productivity through deep penetration, while also enhances solidification cracking susceptibility. To understand these solidification cracking behaviors, in this work, a new methodology has been developed which is able to integrate different components of the cracking issue, such as the alloy composition, welding conditions, and the stress state to determine the cracking mechanisms. And using this model, it has been confirmed that solidification cracking can only occur at locations where we have both tensile stress and sufficiently high strain rate. And because of this complex stress state, cracks only appeared at depths between 70 to 80% of the weld depths. That is all my presentation on this topic. Thank you for listening.